Okay, in this set of videos we're going to learn about calorimetry and how we can use that to find the heat of a reaction. So just as a refresher, in the last set of videos somewhere we talked about stoichiometry. We talked about stoichiometry as a way to find the heat of a reaction. So we've talked about this. When we use this, we are given the enthalpy for a reaction, and then we use molar relationships or molar and gram relationships to figure out the heat for our specific experiment. Now we're going to talk about another way to find how much heat is transferred in a reaction, and it's going to be calorimetry. We're going to define calorimetry as the measurement of heat flow. So this will be an experimental way that we or other people can measure heat transfer in a reaction, or the heat of a reaction, and usually we'll be able to measure heat flow by measuring the temperature change, because the temperature records the kinetic energy of the molecules. If that changes, we can measure our heat. So this is our definition of calorimetry. You don't have this word written on your paper. I want you to write it down, heat capacity. We mentioned this last year. The heat capacity of a substance is the amount of heat necessary to raise its temperature by 1 degree Celsius. So we're going to write that down. This is the definition of heat capacity. It's the amount of heat necessary to raise the temperature of a substance when it's not changing phase. It's either going to stay in whatever phase it's in, solid, liquid, or gas, to raise its temperature by 1 degree Celsius. Now, heat is an extensive property. It depends on the amount of stuff that you have. So you might say, well, how much of the substance? Good question. So we can have something called the specific heat capacity, and we talked about this last year, and this is the amount of heat necessary to raise 1 gram of a substance by 1 degree Celsius. That's the definition of specific heat capacity. And so you can think about, let's get a different color here or something. What if we had just 1 gram of iron? I'm going to draw some, actually I think our iron might be black. I'm going to draw some black iron here. This is 1 gram of iron. And if I needed to add heat to this, so I need to have a little fire under it, there's my flames, and I need to make the temperature go from 18 degrees Celsius only up to 19 degrees Celsius. How much heat, how many joules of energy am I going to have to provide to this piece of iron? Am I going to have to add to this system? That's its specific heat capacity. We can also talk about molar heat capacity. We didn't use this as much last year, but we could. This is very similar. Instead of the amount of heat to raise 1 gram of a substance, the only difference is this would be the amount of heat necessary to raise 1 mole of a substance by 1 degree Celsius instead of 1 gram. This would be the molar heat capacity. But it's the same idea. You're making the temperature of the substance go up by 1 degree Celsius. And again, this is when it's not changing phase. It's going to stay as a solid, a liquid, or a gas, whatever it is. So we're going to focus right now on the grams. We're going to focus on this definition, specific heat capacity. So I don't want to have to rewrite it. So I'm just circling it. And we're going to call the symbol for specific heat capacity, the symbol we're going to use is a big C with a little s, or just a big C. So you could write that down on the paper. That's going to be the symbol for specific heat capacity. That word is capacity. And if we're going to write this mathematically, what we just wrote here in words, we're going to write mathematically. Big C, specific heat capacity, little s, equals the amount of heat, so I'm going to put a Q, Q is for heat, required to raise the amount of heat necessary for 1 gram of a substance, 1 gram, to go up by 1 degree Celsius. So if I need to figure out a substance's heat capacity, I would try to raise its temperature. I would put in its temperature change and its mass and the amount of heat that I needed, and that would give me its specific heat capacity. So a more generic equation for this, I'm going to write it on the next page. I've rewritten my specific heat capacity in a more generic way. I still have the amount of heat required to raise it by one temperature, but if I want to figure that out, I would take a certain amount, certain mass, I would record the change in temperature and how much heat was required to make this change in temperature, and if I divided the heat by the mass times the change in temperature, I'd get the specific heat, just because that's how we defined this. So if I want to figure out the heat, I just algebraically manipulate this, multiply both sides by mass times change in temperature, and my new equation will be heat equals the specific heat capacity times the mass of my substance times the change in temperature. So heat transferred for any substance, the heat that is transferred into it or out of it, like you can think of, we talked about in class well, this was melting, this won't matter. Let's say it's not going to be changing phase, so it would still, if we had some water and we were heating up the water, we're not going to make it turn into a gas. The heat that we'd be transferring into this water from our flame would be equal to the specific heat capacity of the water times the mass of the water times the change in the temperature of the water. We'd have to measure with a thermometer the temperature at the beginning and the end. And that way we'd be able to calculate how much heat did we add to this water over a period of time. So we can calculate heat transfer. This Q stands for heat transferred, whether it's in or out. Now Q will be a positive number if we're adding heat, because if you add heat, this delta T, this is your final temperature minus your initial temperature. That's what this triangle means, change. I'm going to write change here. So this triangle means change in temperature. Change we always calculate by taking the end and subtracting the beginning, or the final and subtracting the initial. So if we add heat, the final temperature will be greater. So this ends up being a positive number, and our heat transferred in would be positive. It's endothermic if we add heat. If heat leaves, then our temperature goes down, so our final temperature would be less. This would end up being a negative number. Our Q then would be negative, and that would make sense because if heat leaves, it's exothermic. So we're going to play with those right now, actually, in a sample problem. So the problem you're going to do in the next few seconds, I actually recorded that slide last year. Hopefully it makes sense. In it, I'm going to give you the specific heat of water, because you'll be calculating how much heat is added to change the temperature of 250 grams of water. And water isn't even on this table. Oh, darn it. So these are specific heats for some metals right here. And they're fairly low. The specific heat of water that you're going to work with on the next page, the amount of heat required to raise 1 gram of water by 1 degree Celsius, this is a specific heat of water, is going to be 4.18 joules per gram degree Celsius, and you'll see that in the next problem. Okay, we're going to work a sample problem using specific heat, and again, we did do this last year. So in this case, the question is, how much heat must be added to change the temperature of 250 grams of water from 25 degrees Celsius to 60 degrees Celsius? I didn't write that there, but these are, let's go to degrees Celsius, okay? So, the temperature is changing. We're not going through a phase change. We're just heating water, so that's an important difference, because if you went through a phase change, you'd have to use the heat of fusion or the heat of vaporization. But the temperature is just rising, so we're going to use the specific heat capacity of water, and this problem, I'm going to give that to you, because it would be given to you in a problem unless you were given everything else and asked to find that. The specific heat of water is 4.18 joules per gram degree Celsius. And our equation that we're going to use, because it's asking for how much heat must be added to raise, and you have a temperature change. And when it asks for heat of a substance and there's a temperature change, you use MCAT. That's what we're going to call this, our specific heat equation. We call it MCAT because it looks like MCAT. I just did this with my regular chemistry classes. MCAT, see, CAT. The delta, you could think, anyway, that's a way to remember it. When something asks for how much heat or energy is needed and it gives you a temperature change, you're going to use this equation. So here our mass is 250 grams. Our specific heat is 4.18 joules, and joules are a unit of energy. And our T final was 60, TF. I'm doing this up here now. And our T initial was 25, so temperature change is equal to final minus initial, 60 minus 25, which is 35 degrees Celsius. Our degrees Celsius cancel, our grams cancel, our units will be in joules when we end up, which is good, and the answer will be 37,000 joules. Now, since this came out positive, which is good because we're heating water, so it should be endothermic. That's good. If it had been negative and we were heating water, we would have done something wrong. So when it says how much heat is added, you should get a positive answer. If it says how much heat is released, you should get a negative answer.